Thanks, Bob. So people say sometimes, okay, say you invented the web, so are you some genius or something, or are you just in the right place at the right time? And I'm going to spend a few minutes making the case that I was in the right place at the right time. And in fact, kind of wistfully, my feeling is that I and the few people of this generation were, in some ways, our particular path that we took through learning about technology and implementing technology, maybe was a one-off. Maybe that's it. If you're younger, and quite a lot of you are, a depressing number of you are, then maybe you've had it. I'm sorry. Maybe you've missed it. And maybe you'll feel about us like I felt about just missing Woodstock and Isle of Wight Festival. Just being a little too young to really get it. I should have hoofed it over there to one of those two places and been there when it all happened, just by a few years, a few months. So my path, I suppose, I started off. Hang on, first of all, I need to know who I'm talking to. So. Seem to have lots of designers and artists and stuff. Could you put your hand up if you have painted a picture or done some other graphic, creative illustration within the last year, in 2010? Who has painted a picture or done something like that? That's cool. Okay, who has improvised music or composed some new music this year, in 2010? Who's written a program this year, including writing? A few. Now, one of my concerns actually is that I found programming really fun, and people are doing it less and less. And that's one of the reasons I'm going to talk to you about what I'm going to talk to you about. So I'm going to go back to when I was in utero. My mum and dad had met, when they were both working in Manchester on the Ferranti Mark I computer. Ferranti Mark I computer came out of Manchester University, and the Mark I computer was very exciting because there were a few people who realized that the programmable computer, as Alan Turing actually proved mathematically, the programmable computer is something different from anything else that's ever been before, because any programmable computer could be programmed to emulate any other one. So they could all do the same set of things. If you could program this computer to do something, you could program that other computer to do exactly the same thing. It may do it more slowly, it might run out of memory. In fact, they tend to talk about infinite computers. But there's this idea that comes out of that a computer can do whatever you can imagine. So as a programmer, this thing, it's not, painting is great. It's a lot of fun, and you get to express yourself with a palette knife and singing is fun, and you get to express yourself. But when you write a program, then you really, imagine that your output is the screen. Anything you can imagine, any form of interaction, any form of calculation, anything that you can imagine this thing doing, it's up to your imagination to program it. You ought to be able to program it if you can imagine what it's doing. That's throwing down a huge gauntlet to the creativity of people. So when I grew up, my parents bought a house in London that they're still in, and in that house they're both basically mathematicians, and so that house was full of how exciting it was, also full of 5-hole paper tape. 5-hole paper tape is good for lots of things. It's good for feeding information into a computer, like in some of the old sci-fi movies, and it's also really good for throwing across the room. If I had to have part of it here, I would throw it from the stage, which is what we used to do in the pantomimes we put on the dining room table. So the world was full of computing, the excitement of it, and also of mathematics, and the fact that mathematics crops up everywhere, and so it sort of was part of life. And so now, I was... as a boy, I like building things rather than playing sports. I'm a geek, by the way, and proud of it. And so when I was in primary school, one of the things that I learned to do, I had this book of experiments by Leonard de Vries. And things that you do from books of experiments that age is if you take a nail and you leave it in the fireplace overnight, leave it hot and then leave it cool down, and then you wrap wire around it and then you attach it to a battery, it will turn into a magnet, and when you unattach it from the battery, it will then turn off. So you can make something, you make a little something which will, for example, set off a gun built like a mouse trap, so you can make a remote control gun for attacking your siblings and things like that, which is very exciting when you're at that age. So I did that, apart from the fact we didn't have a fireplace, so I didn't put the nail in the fire. So I learned some physics, so the metal did not anneal, so when I turned the magnetism on, it permanently magnetized it. And so the gun would fire once. But that was all fun. At that point, you could do all kinds of things with those. Imagine you take a nail and you wrap a little coil around it, and then you can use that coil to operate a switch. So when you put current through the coil, it turns into a magnet, the electromagnet turns into a magnet, and it brings a piece of bent tin in contact with another bit of bent tin, and that will turn something on or it'll turn something off. So that is a relay. So you can use the current flowing in a piece of wire to control another current. You can make it, for example, turn itself off. If you make it so that it pulls a contact apart, then of course it'll turn itself off, which will mean the thing will go back again, and then it'll turn itself on again, and it'll go backwards and forward, and that's a buzzer. So you can make buzzers of all kinds of types and bells, and then you can, and so that in fact there's a whole set of things that you can make out of electromagnets, and after a while you can think of more things that really you've got time to make out of electromagnets. But it happened that as I grew up, and just as I sort of started going into secondary school, it turned out that the transistor, which had been conveniently invented, just as I was being born more or less, the transistor started becoming available in large packets in Proops up the Tottenham Court Road. So I go down Tottenham Court Road and buy these packets of untested transistors, which are basically failed test transistors, but the failed testing wasn't very good. We take them back and do our own tests and sort them into different sort of strengths of transistor, different levels of gain, and we put together these things called breadboards where you stick in transistors and resistors and make circuits. And that actually you can make, to start with, you can make things which oscillate much more quickly than the buzzer. So you can make things that make noises. You can make things which control a train layout. You can make things that will beep for a certain amount of time. You can make burglar alarms. And in fact, out of these transistors, you can make logic gates, which are very much like the relay, that they control more things from just one signal. They can combine signals, so they'll turn on if you have any signal, for example, one or the other, it'll turn on. That's called an OR gate. Or if you build another circuit which will turn on if all of its this and this turn on, that's called an AND gate. And out of AND gates and OR gates and inverters which just turn on when their input is off and vice versa, just to change the sense of something, you can actually build all logic circuits. You can build, anything that you can imagine that's built out of on and off signals, you can make out of, if you want to, nails, but now transistors. You can turn these transistors into gates. And so after a while I started to make things like I wanted to make an intercom with dialing, and as you do that, the number of transistors you need starts to get a bit, you can do it, but you end up soldering a lot of transistors onto a lot of these circuits and making a lot of trips down the Tottenham Court Road to get more transistors. So fortunately, this is where I'm so lucky. Just at that point, when my buddy Nick and I were building these things, and they were getting more and more complicated. And really, building the gates was getting boring. You could now go down the Tottenham Court Road, and you could buy these little bugs. They were called because they look like little millipedes, about an inch long, with pins every 0.1 of an inch, pointing downwards, and each package of those, the 7400, had 4 NAND gates. And if you work it out, actually, you can make anything in the world that uses binary logic out of NAND gates. So, in fact, if you had enough of these little 7400 bugs, then you could make... So that's much more efficient. So we knew, of course, because we'd made all these gates, so we knew exactly what was in them, and because we'd made them out of transistors. We basically knew that if we had to, we could make... And if we couldn't get transistors, which were a bit magic, you always know kind of how the thing worked, because you knew you could make it out of nails and stuff. But now you could get these chips. And so I started building. I decided that it would be kind of nifty to have a computer. Building a computer was a bit out of question. But in those days, computers were big things in racks, which had next to them terminals. So there was a screen, and a keyboard was... the thing that you might think nowadays was a computer actually was just a just a terminal. So there's a thing like a TV with typically with a few rows of print on it and a keyboard. So I decided that I would need one of those. So I started building the visual display unit. That's the thing that displays the characters. I got a TV from the guy down the road for £5. I went in there and sort of said, do you have any TVs where the video piece is working, but the radio piece for receiving television is broken? And the guy sort of rolled his eyes. He's a TV repairman, so went out back and he said, you know, kind of got more than I'd like of those. Have as many as you like. So I took 2. So I was up in my room in the attic, trying to make this TV do stuff. First of all, by putting a signal in going quite slowly, which gives you horizontal bars, and then making oscillators which go faster and faster, and after a while you get vertical bars. And I actually had a feed of the signal going downstairs onto the hall table so that people could see how well I was getting on. And so I got, I come down to lunch and say, hey, you know, you got vertical bars. So, you know, is that better? So then I get vertical bars and go from vertical bars to horizontal bars, and then actually put a logic in to select one vertical bar. So turn the video signal on just for one bar, and then just for one and then put in there a gate, combining those signals that we're in this place and we're in this place, and then have just a block, like a block cursor, which could then be moved around by using a counter. And then after a while, by this time, I'm getting to university. So now in the spare time I'm at university, I worked in a timber yard, and there was a skip where they'd thrown away this old calculating machine that had masses of buttons, and I took those out. And I got to the point where I'd got the whole thing working, except I needed to make what would have been a massive, great matrix of diodes to store the shape of each character. A, B, C, D, E, F, G. The thing has to look up when it gets the code for A, which ends in 1, and the code for B, which ends in 2 in binary. I had to convert that into the actual shape of a B. Now, for every dot, I would have had to solder in a diode. That was going to be an awful lot of dots. But, ta-da, I know, the right generation. Just at that point, you could get a thing called a character generator, which is a built-in, pre-made memory chip about that long. It seemed to cost a lot. I remember £13, but I was much more scared of breaking it than maybe £13 was a lot then. I was frightened. These circuits were very delicate, and you could affect them with static electricity. So I did the whole operation of putting this thing into the board after I bought it with steam, with the kettle going under the table, filling in place with steam, so I wouldn't have any static electricity. And so just at that point, this character generator came on, and so I took it into the lab in Oxford, to the skeptical lab, and I actually got it to the point where it was actually a computer terminal. So at that time I left Oxford. I tested it on the computer at Oxford. And then, ta-da, that's how many years of working toward this goal of more and more complex things. That's just the terminal, right? Okay, it's got the display. It's got the thing in the lid of what you get in the laptop now. And in fact, I could have taken these 7400 series devices and actually made a computer. Because actually I knew how a computer worked. Because the computer is actually pretty simple. It's got lots and lots of memory, and it's got a place, and it's got a little thing to work out on which operation it's going to do next. It doesn't do very many operations. There wouldn't be too many gates, and it has a program counter to work out which memory address it's going to take the instruction from next, and it's got an accumulator, which is where it keeps the number it's working on. And so it's not really actually a computer is of finite complexity. It just is. Once you've figured out what's in a computer, then there are some more complicated ones you can get now, but they're all just equivalent to this really simple one. And then, I'm riding the crest of this wave, because there we are, just as I come to the end of my career by studying physics, by the way, which was fun too, but that's another story. Then it turns out that you could get this slightly longer chip with 40 pins on it, so 2 inches long, which has actually got a complete microprocessor in it. So this 6800 device came out, which had a very nice, beautiful little, nice instruction set processor. So then I saved up, got the thing, and connected up some memory to it, and connected up to the visual display unit, to the terminal. And so just as I was so there I was, leaving. I had 3 years of physics, which doesn't call you a physicist really, but I'd actually felt that I really understood how that computer worked. I programmed it in hexadecimal. Later, I wrote a programming language with it, so I figured out, and there are a bunch of people I know who've got involved with these sorts of things in that, and they've gone through that same sort of stage. And they all know that, they all got that feeling when they look at a computer that actually, they know what's inside it. And so to that point, I went into the, I suppose, hardware, software consulting business. But when I worked for Plessy, went down the South Coast. Went and spent quite a lot of time working with my buddy Kev here, where we understood how these microprocessors worked, and there are lots of people in the hardware field who designed massive racks and racks and racks of electronics of using different sort of technology which is stuck at these various different points, and now you could replace the whole thing with a microprocessor. So there's this huge open field of people who knew how you could do things with microprocessors, and I had a lot of fun going anywhere. So we wanted more or less taking out huge amounts of hardware and putting in software. So the things that Kevin and I did, some of the things we did was we did with printers. We took printers and made them smarter. So we put fonts in them, we put communications protocols in them, we did page layout, and we did macroprocessor limited languages, and we wrote an operating system at one point. So we did all kinds of stuff. And so by the time I arrived at CERN, and I was really frustrated with the documentation of systems, I got all the things I needed to design the web that I designed because I needed it. I was just frustrated it didn't exist. Most of the trouble was persuading people it would be a good idea and not too complicated and worth investing their time in. And so that's the story of how I got there. So I feel to a certain extent, yes, we of that generation were in this, the fact that we followed the new technology. Every time we got to the end of an episode, there was the cake already, that had been cooked in the oven. And now that you've learned how to do it yourself the hard way, now you can get as many as you want the cheap way. So I think that was a really sort of amazing thing, sort of wave to surf in on. And so there we were, and so there I was with the tools to create this web thing. And the reason I told you that whole story is I want you to realize that programming computers, that I want to try and transmit some of what I got from my parents, that programming computers is really, really creative. And what's disappointing now is that a lot of kids in school, the way they meet the computer is not by the same path. They meet the computer like they meet a fridge. It's a white thing, but it's white goods. You open it, you do stuff with it. It has on it Word. It has on it, a spreadsheet. It has on it the web, which for a lot of them open it. Google Facebook login, take the first thing, log into Facebook, and that is what they know of the web, and that is what they know of the computer. That is their world. And they don't know that they've used a search engine, and they don't know that they've used the web, and they don't really know that they've used a computer, apart from and they don't know that if they could imagine the computer doing something different, that they could program it. So the other thing I wanted to say is that actually that when you start connecting the computers together, it's very different. The design is very different, because all that sort of design that you do with sort of building a little mousetrap to fire a gun at your brother. It's like designing a mousetrap in that if you make a better one, you can use it straight away and you can sell it to other people. But now, when you do something on the web, if you design a protocol, like you design, say, the email, suppose you design an email system, you can't just write an email system and set it running on your computer. It's no good unless other people have them. It's like telephones. It's got Metcalfe's law applies that it's the value of one of these things is proportional to somehow positively monotonically related to the number of the ones out there. So that if there's no one, it's very difficult selling the first one. You have to sell it to people who just believe it or relate it or think you're nuts. But certain sets of people who get the gleam in their eye. If everybody did this, it would be really cool. There's a certain type of people under those circumstances where there's something where if everybody did it, it would be really cool. They'll do it anyway. No, they will do it. The early adopters. And in a network, building a network of anything, you need those early adopters. So that is because when you're building something big, it's not just the technical design either. Everything that's been done that over the web has been over the internet, like the design email. It's both a technical design and a social design. Email was designed before I came along. You know, the web is 20 years old, the internet is 40 years old, and somewhere between those 20 and 40 years back, somebody designed email, and they designed email for a system where computers would pass information packages between them like postcards, and everybody would program their computer to happily look after other people's mail and pass it on, because it was an academic environment and everybody was friends. And when the messages arrived, people would read them, because it's an academic environment. If somebody's going to go to the trouble of writing me a message, then I'm certainly going to go to the trouble of reading it. So the system was designed for social setup, which didn't hold when there were millions of consumers online and when you were allowed to use it for commercial purposes. And suddenly the whole system basically broke. I mean, for a lot of people, when spam came, a lot of people just went back to the phone. And for a lot of people now, if they don't have good spam protection, they find email unusable. So when you think about how you design a system, like the web. Now, why does the web work? It works because people follow links. People can only follow links if people make links. Why do people make links? People make links because you make links from your page because you want your page to be a better quality page. You want it to be a better quality page because you want more people to read it. You want people to read it because maybe you want the ads. Maybe you want the kudos. It was all originally done on kudos before you could get ad revenue. So it's the psychology of people wanting to be read that makes them make links to other good things. And when they make links to other good things, then by doing that, they're actually voting for those other good things. And the links themselves form this huge mass of critical review, which is actually how the web works. And the search engines aren't smart. They just use that massive critical review put in by human beings. So the search engines all rely on those links critically. So it's all about people. The system is a social, technical thing, and the design of the technology and the design of the social piece of it absolutely intimately linked. And if you want to design a new social networking site, or you want to design a new protocol, or you want to design a new peer-to-peer thing, or a new instant chat, or whatever it is, whatever you're just about to think of, okay, you're designing a human system mediated by technology. And it looks as though you're designing a piece of technology. You're designing a new way two computers can talk across the internet, but really it's not interesting unless it ends up designing a new system. The reason I say it's not like designing a mousetrap is that when you design the small system, it is completely different. It's a system that links how two people talk, or how two people, one can put something up for auction, another person can bid on it. You design that as a microscopic thing. As a result, with eBay, eBay did work. So the result is you get this macroscopic phenomenon that there is an open market for all kinds of second-hand junk, which probably had a huge economic effect on in raising the value of second-hand junk and lowering the cost of second-hand junk to the people who need it. So eBay, then, apart from making a few people pretty rich, it actually made a lot of people's lives easier. And it allowed lots of things to happen, and it changed the economy because it produced a system which which spread because it worked and it was good. One of the things that concerns me now is we all use the web, we all rely on it, and we're all actually, as people, we're intimately connected in with all kinds of systems. A lot of us, we come here and we sit in this teepee, which is very nice, and it's it's very much rock and stone and back to the elements and stuff. But we all used maps in our cars, and satellite data to get here, and we looked it up on the web, and we probably found lots of stuff about it on the web, and we got here directly through email. So we're very much connected, and a lot of our jobs depend on this web thing, and a lot of things, the way people vote depends a lot on this web thing. Whether people believe in science or cult religion depends on this web thing, and we don't really study it. So we know that the emergent phenomena which happen out there on the web. So what's trending, the fact that things trend on Twitter and decay, are all a result of the things that we've been doing on a microscopic scale. But we haven't really got any mathematics. We haven't got people studying the web as a big thing. So if you're the younger generation, if you maybe grew up not realizing this computer was something which you must start programming right away, maybe you should use what use your creativity and and all the brain power you can possibly throw at, not just looking at a computer, because now you've got a responsibility to now look at this big thing, the web. It's actually, now there are as many web pages out there. There are 10 to the power 11. That's as many neurons as in your brain, the web. If you could take it in, I could bring it down here and bring it down to brain size. It's a very complex thing. It's not the shape of a brain. We don't understand it. We don't know what shape it really is. I don't have any pictures of it. And we don't understand whether it's actually going to be stable in the future. So, those are the two things I wanted to tell you. Okay, that computers are a lot of fun and you should program them. But when you program them and connect them together, it's not like programming one computer. You have to think about the whole mass of 10 to the power 11 things, and that's, of course, why it's so fun and exciting. Thanks.